Hi, folks. Today we're going to talk about calculus as it relates to derivatives. And so we've already introduced some of the basics, but let's review a little bit first. And so the ancients struggled with the idea of movement because all of their math focused on static, unchanging objects. And so in particular, they didn't have the geometry or functional analysis needed to figure out rates of change. With Descartes, we got analytic geometry. And analytic geometry gave us a new tool set and a new geometry to play with. When we add in the work of Galileo and Copernicus, there was great interest in developing calculus, some new mathematics to understand how things move, grow, or change. With the new tools of Descartes, calculus ideas started to form among the great mathematicians. In particular, Isaac Newton and Gottfried Wilhelm Leibniz created independently are credited with independently developing calculus in the late 1600s. There were many others who contributed, but those two, they really got the ball rolling. Because it took decades to work through and publish findings, there was quite a bit of drama about it at the time as far as who should be credited with it. Newton was in charge of a society at the time that said, no, Leibniz gets no credit. Whereas Leibniz and the Germans, I believe it was, ended up saying, no, Leibniz should get all of the credit for it. It was a mess. In the end, Newton got most of the credit, but in practice, we use Leibniz's version of calculus, as well as a few others who contributed. Calculus, at its core, is the study of how things move, grow, or otherwise change. To understand it, we needed a few tools. We needed analytic geometry, which related graphs and functions, and we needed an understanding of infinity, of small numbers and closeness, and of continuity and connectedness. Those are the things we talked about last time. The remaining steps towards calculus are just putting the pieces together. We need a reference frame to determine how things move, and we can just use the Cartesian coordinate system to do that. We need to figure out rates of change of curves from that reference frame, and then we can play with the structures we create. That's really what calculus is all about. It's all about trying to figure out rates of change of curves, and then trying to figure out what other things you can figure out. And so let's talk about difference quotients. What is the rate of change of a function? And so remember back from Algebra 1, we learned about slope. And so the slope is the rise divided by the run. It is the rate of change of a line. But the challenge is it's a line. It's not a very interesting structure. What if we were dealing with a curve? What about a quadratic? What if we had a function which was f of x equals 1 over x, or maybe a trigonometric function? We can't simply do rise over run. We'd have to do some more steps to it. And so that's where our next ideas come from. The idea of the difference quotient. And so if a function is not a line, we still want to think of the slope. To do so, we use difference quotients. A difference quotient is the quotient of the change in the y direction and the change in the x direction, which is really what our slope was. It's just we have to have a couple of points in order to figure out the difference quotient. It's the slope of a line connecting 2 points on a function. So in this example, given f of x equals x squared to the right, we can consider the 2 points -1, 1 and 2, 4 and find the slope of the connecting line. The slope is called the difference quotient. And so looking at this green line, what is the slope? Well, you can probably just eyeball it. As you're going over 1, you're going up 1. 1 over 1, this has a slope of 1. Now, if we don't have a nice graph, what we can use is formulas. And we have two main difference quotient formulas. The first one looks nicer. The second one actually is nicer. And so the first one is actually the same thing as our slope formula. This is f of x2 minus f of x1 over x2 minus x1. Really, you can think of this as the slope equation. It's y2 minus y1 over x2 minus x1. And so if you have 2 points, you can just plug the y values in, plug the x values in, and you get your difference quotient. The problem with this one is you need 2 points. What we would really like is we would really like to figure out the difference quotient using only a single point. And that's where the difference quotient comes in. And so the difference quotient, formula 2, given a continuous function, the difference quotient at a, which runs h units, is given by this, f of a plus h minus f of a over h. And so in this case, instead of saying we have an x1 and an x2 value, we're saying we have some starting point and then we have some run. And so this h value is really equal to x2 minus x1. It's our endpoint minus our starting point. But we can just think of it as the run. The reason that makes it nicer is eventually we're going to try and make it so that this run disappears and then we're left with just a single value, just a slope at an individual point. That's the real power of this second formula. And we'll see how that works in just a minute. For now, let's try a practice problem. Let f of x equal x squared on the interval -1, 3. Find the difference quotient. If you want, you can pause the video and try those formulas out. If you'd like, you can just look at the graph. I mean, looking at the graph, we can see what the answer is. What is the slope of the line connecting those 2 points? Well, you go up 2 and over 1, so this is a slope of 2. Now the question is, do our formulas give us 2? Using our first formula, our line goes from -1, 1 to 3, 9. And plugging in those values into our formula, we have 9 minus 1 and 3 minus -1 gives 8 over 4, which is 2. And so the difference quotient is 2. If instead we used our second formula, it might look a little more complicated, and that's because it is, but it'll clean up very nicely. And so our starting value is a equals -1. Our run is 4 because we're going 4 units from -1 to 3. So plugging this into the formula, we get f of -1 plus 4 minus f of -1 over 4. Well, -1 plus 4 is 3. F of 3 is 9. F of -1 is 1. So it's 9 minus 1 over 4 is 2. And so, nope, we got the same answer, which is good. And it's the same answer we got when we just looked at the graph. And so all of this seems to be checking out. The true benefit of the second difference quotient formula comes from asking what happens when we let the run h go to 0. And I've got that marked off here in blue. And so this first green line, that's the difference quotient we just did. Then we have the difference quotient we've done before that. If we let it so that this point, this second value, gets closer and closer and closer, eventually we will get what we call the instantaneous rate of change. Essentially, what happens as h goes to 0 in our difference quotient formula? What happens as the run goes to 0? Now, obviously, we can't just plug 0 in for h, because then we would divide by 0. But we know that this limit is going to have a value because there's definitely a line which is tangent. And so what is the slope of this tangent line? Well, again, we can kind of eyeball it in this case. Looking at it, it looks like we are going down 2 and over 1. And so we should get a slope of -2. If we evaluate this limit at -1, we would expect to get that slope of -2. And so let's see if that's what happens. Find the instantaneous rate of change of f of x equals x squared when x equals -1. Well, we got a lot of algebra to do. And so the formula we have to evaluate is f of a plus h minus f of a over h with the limit as h goes to 0. Evaluating the numerators, we get f of a is -1. F of a plus h would be -1 plus h squared. We can do a little bit of algebra to clean that up, but we might as well wait. So plugging these into our formula, we now have the limit as h goes to 0 of f of a plus h minus f of a over h, which is -1 plus h squared minus 1 over h. We can FOIL the stuff which is squared. We can then cancel the ones out, and we can factor an h out on top, which gives h times -2 plus h over h. Well, we can cancel the h's, and then as h goes to 0, this h goes away also, and we're left with -2. And so the instantaneous rate of change is -2. Going back to look, that's what we had. When we look at this blue line is the line tangent at that point, and the slope of that line is -2. If we have the instantaneous rate of change at a point, then we have all the information needed to write the equation of that tangent line. And so point slope form is very nice for this because we'll have the slope and we'll have a point. And so in the case of x squared at the point -1, 1, we could write this line as y minus 1 equals -2 times x plus 1. That's the equation of this blue line, and it's tangent at that point. We sometimes call this tangent line the linearization or linear approximation, and sometimes we write it in this format, f of a plus our slope times x minus a. Really, that's just point slope form, but with the y1 value moved over to the right so that it's in an explicit format. All right, so now we are ready for the derivative. Let's do it. 1 point is not enough. And so the instantaneous rate of change gives the slope of the tangent line given by that formula. Typically, we want to understand the slope at more than 1 point. And so looking at this, I've drawn out the tangent lines at a variety of points. And we can see that the tangent lines, the slope of those tangent lines is changing as we're moving. Given a function f of x, we call the derivative f prime of x, the function which gives the instantaneous rate of change at every single point. And it's given by almost the same formula. F prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x over h. This is just our difference quotient. This is just our slope formula. This is rise divided by run. And so rise over run. And then we're saying what happens as we let the run go to 0. This formula will tell you what happens at every single point and give you the slope at every single point on a curve. And so here's an example. Consider the function f of x equals x squared. Find the derivative f prime of x. Well, all we have to do is evaluate that formula. And here's the work. And so we're starting with our formula. F prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x over h. We can evaluate the numerator just like before. F of x is x squared. F of x plus h would be x plus h squared. We can then plug it all in. And so we will get this limit is equal to the limit as h goes to 0 of x plus h squared minus x squared over h. Well, just like before, we can FOIL out the x plus h squared, and then we can cancel the x squared terms out. After we cancel the x squared terms out, we can factor an h out of the numerator. And then we can cancel the h in the numerator and the denominator, leaving 2x plus h. As h goes to 0, that leaves us with 2x. Therefore, the derivative is f prime of x equals 2x. That expression 2x tells us the slope at every single point on the curve. And so given a function, the derivative tells us what the slope is at any given point. In our example, we found the derivative of x squared to be f prime of x equals 2x. This means that if we evaluate this 2x, that'll tell you the slope at any point on this curve. And so when x is equal to -2, the slope is -4. So at this point here, the slope would be -4. if we, I went too far, there we go. At negative 1, 1, and so that's the one we just did, the slope would be negative 2. At 0, well, plugging 0 in, we're going to get the slope is 0. When x is 1, we get a slope of 2 times 1, which is 2. And when x is 2, we're going to get a slope of 2 times 2, which is 4. Congratulations, you just learned calculus. That's it. That's the entirety of calculus right there. Or at least the start. That's Calc 1. The idea is we can find the rate of change of any function, and it doesn't matter how messy the function is. And so the rest of calculus is just about trying to understand all the different types of formulas that can arise, but it all goes back to this idea. The derivative is just this limit as the run gets really, really small of rise over run. And we can think of rise over run in the terms of lines. And so there's very little difference between finding the slope of a line and now finding the slope of a curve. Notations. Oh, there's always notations. And so because calculus has been used and reinvented for different things throughout the years, mathematicians use different notations depending on their application. And so Leibniz, he viewed the derivative as a rate of change. And so he would usually use dy over dx to represent that it's a ratio, which is what it is. Newton, he saw the derivative as a component in some greater structure. And so usually what he would be using it for is he would say, what's the change in the x direction? What's the change in the y direction? What's the change in the z direction? And he would use a dot to represent the derivative. And that way it wouldn't take up too much space. So if you're dealing with 3 or more dimensions, you just have to put a few extra dots here and there. Euler thought of the derivative more as a transformation of functions. Because if you think about it, what we did in that last example is we took x squared and we transformed it into a new function, which was 2x. In thinking of it as a transformation, he used the standard transformation symbol, which is just a capital letter, kind of like a large T or a function notation almost. And so in this case, the capital D is saying we are going to transform whatever function y is. And then Lagrange, well, Lagrange just said, hey, it's a function. Our derivative, it's some new function. And so he just used a prime, an apostrophe to represent the derivative. And that's probably the most common one, is using a little prime symbol to represent the derivative. I said the most common notations are from Leibniz. I like Lagrange better. And so differentiation formulas. We can take the derivative of any nice function. And by nice, I mean continuous. Continuous functions are great. But even if there's discontinuities, we can usually still take the derivative of it. To the right is a list of core rules for differentiation. Using things like the chain rule and product rule, we can take any combination of functions from algebra or trigonometry and find their derivative. If we're dealing with inverse trig functions, it's not a problem. We got a logarithm, which is composed with a tangent, and let's say that all of that is multiplied by an inverse cosecant. That's okay. We can find the formula for the derivative of it. And these formulas are shortcuts that make it so that we can do it very, very fast. A large portion of Calculus 1 is about memorizing all of these different formulas. And so here's a couple of practice problems. The first one is using the difference quotient definition. The second one is just using the differentiation formulas. And so if we wanted to find the derivative of sine of x, well, we could just go to the list and say derivative of sine of x is cosine of x, and we're done. Or we could prove it. And so here's the quick proof. It's the limit as h goes to 0 of sine of x plus h minus sine of x over h. We have a rule which allows us to separate sine of x plus h into these components. At that point, we can separate out the x terms and the h terms, and then just take the limit of the h terms. It turns out this term is going to go to 0, and this term is going to go to 1, which means we're going to be left with cosine of x times 1, which is just cosine of x. I do not in any way, shape, or form expect you to have that memorized or be able to do that on a test. We are a survey of math course, and so we're just trying to explore some of these topics. Same with this one. This is a very complicated looking function. It's a natural log times the cosine of 2 to the tangent of square root of x. Well, by the time you finish calculus 1, you'll be able to take the derivative of it very, very quickly. And this is what the derivative looks like. It's a very long thing. It's cosine of 2 to the tan root x over x minus all of this stuff. And so it looks very, very complicated. But with the tools of calculus 1, it's not terrible. So now that we've seen that we can do all this stuff with formulas, the big question is, why do we care? And so what are the applications of derivatives? Why do we worry about this stuff? Well, let's start with Newton. Why did Newton care about calculus? Well, Newton cared about derivatives for the purposes of physical motion. And that in and of itself was a good reason to establish the derivative. He developed an entire branch of math just so that he could understand the motions of the universe. He reasoned that the motions of the planets and stars followed the same rules as the motions here on Earth. But again, there wasn't math to describe that really. And so what Newton did was he developed calculus just to model these motions. We often refer to this as Newtonian physics or classical physics. And he was able to show that the motions of the stars and the motions on Earth are all the same motions. It's all differential equations which describe how things move. The idea of forces and how forces are able to cause movements. The derivative represents the rate of change or the motion of an object. We also have higher order derivatives though, and these can have a little bit more impact, particularly in the physics world. And so when we take the derivative of the derivative, we get what's called the second derivative. In motion, the second derivative represents acceleration. So how fast is something getting faster, or how is it decreasing in speed? In physics, it helps model forces, such as gravity. Force is often defined as mass times acceleration. And acceleration is just this second derivative, the derivative of the derivative. If instead we're thinking of a graph, the second derivative will tell you how something is curving. Is it curving in an upward direction or curving in a downward direction? We can also explore higher order derivatives. The acceleration usually gets you pretty far. But the third derivative would be the jerk force. After that, I think fourth, fifth, and sixth are snap, crackle, and pop, because whoever came up with the names thought it was kind of funny. Other applications, though, beyond physics, I mean, biology is a very large one. A differential equation is an equation which has a derivative in it. And usually when we're talking about biological processes, we're talking about structures which have the property that the rate of change is somehow proportional to the population size. A key example is bunny rabbits. And so the more bunny rabbits you have, the more bunny rabbits you're going to get. They're going to reproduce at faster rates when you have more bunny rabbits. And so when we're trying to model stuff like this, we usually are trying to tie the rate of change to the populations themselves. And this is a very large part of biology. For example, this system over here, this is called the Kermack-McKendrick epidemic model. We use it to model everything from COVID to chickenpox. And with enough practice, you'll be able to recognize exactly what every single one of these terms means and why they have to be in this system. This system describes how people get sick, but any biological process or system in ecology can be modeled using this type of system of differential equations. And so you see this pop up a lot. We can also use derivatives to understand graphs. And so when we want to understand a graph, or what we expect behavior to look like, we can consider the curvature of a function. And so sometimes we call this concavity. And so concavity is related to the second derivative, and it can tell us if a function is curving up or curving down. This can be used to analyze trends modeled by statistics, including economic and political trends. And so is something starting to turn around? Is it flattening out? And do we expect it to turn back up? Or is a trend finally reached its peak and it's starting to decrease? Depending on what trends or types of things you're analyzing, seeing this type of structure and being able to understand curvature can help us understand when something is going away or when something is starting to turn back. We can also solve any equation. And so Newton came up with a technique where you can use the derivative in order to solve basically any equation. And that's kind of fun. And so let's suppose that we have some random equation and we have no idea what the solution is going to be. Maybe it's something which is impossible to solve using algebra. Well, if we can rewrite it as a function which is equal to 0, which we can do with any equation, we can just move everything over to one side. Well, if we create the linearization at some guesstimate, some guess that we have, our linearization is going to give us some new, better approximation. Well, if we repeat that, then the new approximation from that approximation is going to be an improvement as well. If we do it again and just repeatedly apply this linearization process, we very quickly get to an answer which is very close to the actual value. Usually by the time you've done this 3 to 5 times, you're going to get up to 10 decimal places of accuracy, depending on where you started. And so using derivatives, you can solve any equation very quickly. Another tool is optimization. And so if we ever want to get the best of the best or the worst of the worst, it turns out we can use optimization. Well, in general, things are going to be optimized when they're at their peaks or their valleys. And so all we have to do is figure out where things are going to be flat. And so where is the slope flat? Well, that would be when the derivative is 0. And so if we want to find the high point or the low point of anything, all we have to do is take the derivative and set it equal to 0. This is true in business optimization too. And so in business and economics, we typically want to optimize profit. Profit is the difference between revenue and cost, both of which can be modeled using functions. Of course, it's not always as easy as taking the derivative, but understanding the equations can help determine if there are other modifications that can be made to make a business or to a business to increase profit. And increasing profit, that's usually going to be one of the big goals of business, for better or for worse. And so understanding what happens when we take the derivative and set it equal to 0, that will help us understand the structures of our business. Final thoughts. Oh, calculus is a big topic. And so since derivatives are rates of change, they can be used to model anything that moves, grows, or otherwise changes. In your field, what do you analyze which moves, grows, or otherwise changes? And can you create a function to model it? We often use differential equations to do serious modeling, and the behavior of these differential equations model our reality. And so looking at this one over here, have you ever seen a graph that looks like this one? This is a system of differential equations, and you see systems of differential equations describe the nature of most things that move. A lot of people will look at something like this and say it looks kind of like a weather pattern. Well, it does, because weather patterns follow this idea. As weather changes, as atmospheric pressures are moving, as clouds are moving, it's all just this idea of things moving in different ways. And if we can understand how things move, how they grow, how they change, we can understand the nature of just about everything around us. With that, I'll let you get to work exploring where you find derivatives and rates of changes in the real world. Good luck, folks.